So first let us know the terms used in a naval ship. So this is a schematic diagram given in a textbook about a naval ship. So this is your top view of a ship. When viewed from the top, your ship looks like this. When viewed from the front, if you stand in the harbor and see the ship, it will look like this. Okay. So your propeller is like this. A propeller. So the front end of the ship is called as bow. B-O-W. Bow. Front end is called as the bow. The rear end is called as the stern. Okay, so always in many problems, most of the problems, your propeller is here in the front end. Okay, it is assumed like that. Okay, propeller is in the front end. Normally in ships it can be either way. The propeller can be in the front as well as the back. Okay, if your propeller is in the front, it will pull the ship. It is at the back, it will push the ship. It can be in either way, no problem. Okay, so normally in these ship problems in your syllabus, you look at the propeller rotation direction from the back of the ship, or looking from stern, your rotor goes around in clockwise or anti-clockwise. What will happen if you look from the front? It means that you are looking from here, the direction will reverse. If I look at the propeller from the bow and it is anti-clockwise, the same case, let us say you are having a propeller, it is rotating in this direction. Okay, now if you look from the front, this will look as anti-clockwise, but if you look from the back, it will look as clockwise. That you have to remember very carefully. So for a same case, exactly same rotation of the propeller can be started as clockwise or anti-clockwise depending on from where you are observing it. Okay, if you look from the back, if it appears clockwise, same if you look from the front, it will appear anti-clockwise. So you have to read the question very carefully. So the front end of the ship is called as bow, rear end is called as stern. Okay, so the top and the front views of a naval ship are shown in below figure. The fore end of the ship is called as bow, rear end is called as stern or aft, but we are normally using the term stern. It can also be called as aft. Okay, so rear end is called as stern. Okay, the left hand and the right hand sides of the ship when viewed from the stern, if I stand here, the left end of my ship is called as the port side, P-O-R-T, port. Okay, and the right end of my ship, right hand side of my ship is called as the starboard side. Okay, normally if you see the docks, in the docks of a harbor, your ship, the dock will be like this. There will be a lot of water here. Your ship will be parked like this. So the left side of your ship will be your port side, harbor side. You will put all the goods down like this. The right side you will have water. You can see the skyline, horizon. So that side is called as the starboard side. Okay, remember this. This is very important. You have to remember these words. I will repeat. The front end of a ship is called as bow. Rear end is called as stern. When I stand here and see, the left side of my ship is called as port, and the right side of my ship is called as starboard. So these four terms you have to remember very carefully. Now with this propeller going around in clock in some direction, with that if I steer the ship, steering means turn left or right, what will happen? So if I pitch the ship, pitching motion, your ship will go like this. It will oscillate. Okay, all these things you will see now. And rolling motion. So if you turn, so sway to the left or right, what will happen? So all these motions. Other than these, there are some other motions in a ship, which is not in your syllabus also. All those motions you can see here. So this is the pitching of a ship. Okay, rolling of a ship, heaving of a ship. Heaving is not in syllabus. Okay, surge is also not in syllabus. Yaw is in syllabus. Okay, this is yaw. Yaw motion. Swaying is not in syllabus. So you have to see what is rolling, pitching, and yaw. I let it play once again. See what is pitching motion, rolling motion, and yaw. So these three things you keep in mind. I let this animation play once again. You please concentrate on what is rolling, pitching, and yaw. Pitch, roll, yaw. So these things you have to keep very clearly in mind. Now what will happen? My propeller is already going around in a clockwise or anti-clockwise direction. Now with that, if I pitch, roll, or yaw, what will happen? All the three cases we are going to see now. Okay. So effect of gyroscopic couple on a naval ship during steering. Okay. So my propeller is already going around. With that, if I turn the ship to left or right, what will happen to my active couple, reactive couple, how it will react on the ship, all those things we are going to see. Okay. So steering is turning of a complete ship in a curve towards the left or right. Steering is something like, yeah, you are horizontally turning the ship while it moves forward. Consider a ship taking a left turn and the rotor rotates in clockwise direction when viewed from stern. That is, when you look from the back end of the ship, the propeller is going around in clockwise direction as shown in figure below. The effect of gyroscopic couple on the naval ship during steering, taking a left turn, may be obtained in similar way as discussed in an aeroplane case. Okay, so when the rotor of a ship rotates in the clockwise direction when viewed from stern, it will have its angular momentum vector pointing in the OX direction. Okay, so when my rotor is going around in clockwise, its angular momentum will point like this. Now, if you take a left turn, your new angular momentum will point like this after when you have started turning. So this is your angular acceleration. Okay, it's a change in velocity. Okay, so same thing. We'll have some two figures in the next page. You see here, this one I am telling. Okay, so initially when your propeller is, when you are going in a straight line, your propeller angular momentum is pointing like this. After you have started steering, your angular momentum, the current angular momentum is here. So this is your angular difference. It's your active couple. If you apply some couple only, this will happen. You have to spend some effort to turn the ship like this. Okay. So as the ship steers to the left, the active gyroscopic couple will change the angular momentum from OX to OX dash. The vector XX dash now represents the active gyroscopic couple and is perpendicular to OX. So that is this. Okay. So this is your initial angular momentum position. So now current position. So this is your active couple. This much active couple I am applying. So I'll get a reactive couple in the opposite direction. Numerically equal reactive couple in opposite direction in an orthogonal axis. That is very important. Okay. So thus the plane of active gyroscopic couple is perpendicular to XX dash and its direction is in the perpendicular direction, orthogonal direction. For left hand turn in clockwise as shown in figure below. So this is yaw motion. I am horizontally turning the ship on water without doing anything else. Okay. So the result of this, when you are having a propeller going around and you are taking a turn on left or right, what will happen? It will pitch the ship. The reactive couple will pitch the ship. Okay. So effect of this reactive gyroscopic couple is to raise the bow or lower the stern. Okay. So this case you have to very carefully remember, when my propeller is going around, my rotor is going around in clockwise direction, as I see it, I am standing at the back end of the ship. Okay, and I am looking at the propeller at the front end of the ship, which is going around in clockwise direction, and I am taking a left turn. What will happen? It will raise the bow and lower the stern. It will pitch as a result of this turning effect. So that is your reactive gyroscopic couple. Clear? Active is what you spend the energy to turn the ship like this. Some energy is spent to turn the ship. Reactive couple will raise the front end of the ship and lower the back end of the ship. So that is your reactive gyroscopic couple. Okay. So this is your active couple, what you do, and the end result because of the gyroscopic effect is this. The ship will start pitching. So because of this steering effect, you will get the pitching effect. Now, if your rotor is going around in clockwise and you take a left turn, and when I see from the back my rotor is going clockwise and I take a left steer, my effect of that reactive gyroscopic couple is to raise the bow and lower the stern. Okay, so from now on I will take only bow and stern. I will not say front end, back end. Bow means front end, stern means back end. Okay. So there are some various cases. There are various possible effects. Okay. So what I have done is, if I read all these points, you will not remember it. So raise the bow, lower the stern, raise the stern, lower the bow. All these things will be very confusing to you. So what I have done is, I have put a complete table as we did it in your aircraft case. Now in this table, so rotor viewed from back end or front end. So rotor rotation direction. What will happen to the, which side you are turning? So what will happen to the bow? What will happen to the stern? So I will give you a complete list. So if you remember this list, your problem conclusion statement is very easy to write. So my rotor, I am looking at the rotor from back end of the ship. My rotor is going around in clockwise direction, and now I am taking a left turn. So that will lift my bow and lower the stern. Okay. Same thing when I look from the stern and my rotor goes around in clockwise direction and I take a right turn, the opposite will happen. My bow will fall lower and the stern will rise. Okay. The same thing in opposite sense. Now when I look at the rotor from the stern, and my rotor goes around in anti-clockwise direction, okay, opposites will happen. Now I am taking a left turn. What will happen? What happens in clockwise right turn will happen in anti-clockwise left turn. So this result will happen here. Okay, this result will happen here. So therefore your bow will lower and stern will rise. Similarly, when you are looking at the propeller from the back and the stern of the ship, while the propeller is going around in anti-clockwise direction and you are taking a right turn, what will happen? The same that happens in the first case, left will happen here. Okay, your bow will rise, stern will fall. So same thing when I look from the front end of the ship or from before the propeller, if I look, so those things I am writing here. So if I look at the propeller from the front, okay, bow, the rotation direction is clockwise, means it is actually anti-clockwise if you look from the back. So what will happen? These two results will come here, this result. So when I looking from the front, it is actually anti-clockwise. When you look from the front, it looks clockwise. When you come back, it is anti-clockwise. Okay, so this effect will come if you take left, and this effect will come if you take right. For clockwise here, when look from front, for anti-clockwise, this result will come. Here, the effect is same. Where you are looking from is different. So I take a left turn. What will happen? So my bow will lower and stern will rise. Similarly, if you look from the bow and clockwise rotation, take a right turn, your bow will rise and stern will lower. So these two are these two. They are exactly same. Because propeller is rotating. When I look from the back, what is happening? It seems to be in clockwise. Same thing when I look from the front, it will look in anti-clockwise. So that same result I am writing here. Similarly, these two results will come here for anti-clockwise case. Okay. So question should be read very carefully. Where you are looking from, in which direction the propeller is appears to rotate. Okay. So look from the bow, anti-clockwise is actually clockwise. Okay. So same first two results will come here. Raise the bow, lower the stern. Similarly, anti-clockwise, take a right turn, it will lower the bow and raise the stern. Clear? So any doubts in this table? So if you remember this table very well, you can write the conclusion statement very easily. The conclusion statement is very crucial for you. That shows your understanding of the problem. Okay. So now during pitching, what will happen? So this is the pitching motion of a ship. This is the pitching motion of a ship. If my rotor is going around and I pitch the ship, what will happen? So it will roll naturally, right? If you roll, if you steer, it pitches. If you pitch, what will happen? So we are going to see that pitching moment is this GIF image. You can see what is pitching moment. When the propeller is going around and I pitch the ship, the pitching is assumed to be simple harmonic motion. Okay, and it is actually about the mean position. Pitching above and below is assumed to be symmetrical. Mostly it will be symmetrical only, and this motion is assumed to be simple harmonic. So with these assumptions, angular displacement of the axis of spin from the mean position in t seconds is phi sin omega t. Since it is your simple harmonic, this simple harmonic form comes in phi sin omega t. So phi is the amplitude of swing from the mean position, 1/2 of the theta. Okay. Omega 1 is the angular velocity of the simple harmonic pitching velocity. Okay. So precessional velocity is d theta by dt. Differentiate the above equation, you will get phi omega 1 cos omega 1 t. So angular velocity of precession will be maximum when this cos theta becomes 1. This entire thing becomes 1. Then only your value will be, this value will be maximum. What value? Precessional velocity will be maximum when cos theta component becomes 1. Okay. Otherwise it will be less than 1 on all the other cases, for all the other values. Okay. So therefore maximum possible value of precessional velocity is phi into omega 1. Clear? If a problem, if they ask what is the maximum possible value of precession, then you have to just multiply this angle and the pitching velocity. Pitching angle and pitching velocity. Okay. So angular velocity of precession will be maximum when this is 1. Therefore, if you put 1 in above case, it becomes phi into omega 1. In place of omega 1, I am substituting this simple harmonic formula 2 pi by. So these things we have seen extensively in the vibrations unit. Okay. 2 pi by Tp gives you the angular velocity. Okay. Let I be the moment of inertia, omega be the angular velocity of the propeller or rotor. Maximum gyroscopic couple is again I omega p max. Omega p max is phi into omega 1. Just now you have seen here omega p max in the last line. So omega p max is 5 into omega 1 or 5 into 2 pi by Tp. This Tp is the pitching time period. What is the time taken for the ship to rise, fall and come to the mean position? From mean position, rise, fall and come back to mean position. That is the time period of pitching. Okay. So I omega, same formula, I omega omega p. No change in the formula. Gyroscopic couple, maximum active gyroscopic couple is I omega omega p. So same diagram. I don't think you need explanation for this again. So when pitching is upward, the effect of reactive gyroscopic couple as shown in figure B will try to move the ship towards the starboard side. On the other hand, pitching downward, the effect of reactive gyroscopic couple will turn the ship towards the port side. So the result is rolling. This is the reactive gyroscopic effect. When the propeller is going around and you pitch the ship, the end result will be rolling effect. The reactive couple will try to sway the ship to the left and right, roll the ship. Okay, so at what case what will happen? That again we have to see here. All these notes, many cases are given. Maximum acceleration pi into omega 1 square. Okay. Again, this tabulation you will see what will happen during pitching. So rotor viewed from rotor, direction of rotation, bow direction, rolling direction. Rolling is the reactive part of the component that comes as a result of the gyroscopic couple. Okay. So when I view the rotor from stern and the rotor goes around in clockwise direction and the front end of my ship is going up and going down, falling, what will happen to the ship? In which direction it will roll? My ship will roll towards the left or the port side. Okay. My ship will roll to left. When you are looking at standing at the back end of the ship and looking at the propeller is going around in clockwise direction and you push the ship, the front end of the ship is going down, and as a result of that, as you have two rotations, one rotation is the propeller rotation, second rotation is your pitching rotation about the perpendicular axis of the propeller axis. The third rotation comes, your ship will roll to the left, port side. Okay, you should not write left, you should write as port side. Similarly, stern clockwise, when your front end of the ship is going up, is rising, the ship will turn to the other side, starboard side, right side. Your ship will roll to the right side, starboard side. Same thing, anti-clockwise, opposite results will come. Okay, when I look from the bow, anti-clockwise, same two results will come here. Same results will come here because clockwise seen from stern and anti-clockwise seen from bow are exactly same. The propeller, you are standing at the back of a fan and see that go to the front, it will appear in opposite rotation. Okay, same results will come. So when you are falling, port side, rising, starboard side. Okay, now looking from stern, clockwise rotation. Now stern is falling. So front end is rising means back end is falling. Any type the question can be asked. In the question they can tell the bow is falling, or the bow is falling means the stern is rising. Okay, front end of the ship is going down means the back end will go up. Back end is falling means the front end will go up. Same question can be asked in any way. That's why such a large tabulation you are getting. So when I look from the stern, rotor is clockwise and the back end is falling means front end is rising. This result you will get. Okay, only the manipulating the words, the result exactly, there are only two possible results. Either ship will roll to the port side or the starboard side. The question can be asked in many ways. That's why I have given you a large table. So that result will come here. The ship will roll to the starboard side. Similarly, stern, clockwise, the back end of the ship is rising, you will get port side rolling. Bow, anti-clockwise, same results will repeat. Okay, I hope you understood all these. Rolling result of pitching the ship when the propeller is going around. Similarly, the third case, when you roll the ship with the propeller going around, what will happen? Okay, so nothing will happen. Why? We know that there are we know that for the effect of gyroscopic couple to occur, the axis of precession should always be perpendicular to the axis of spin. If however the axis of precession becomes parallel to the axis of spin, there will be no gyroscopic effect. Which means what? My propeller is rotating, and if in the same axis of rotation of the propeller, if I roll the ship to the left and right, now your active couple and the propeller rotation direction are exactly the same. They are rotating in the same axis. Now my ship is rolling like this and there is a propeller in the front and the propeller is also rotating in the same plane. In the same plane you are swaying the ship to the left and right. So both happen to be on the same axis of rotation. Therefore there is no gyroscopic effect. For gyroscopic effect to happen, the rotation spinning should occur in one axis, and you have to rotate or roll or pitch the ship in the opposite, in a perpendicular direction. Only then the reactive couple will come. In this case, there is no gyroscopic effect. Clear? Do you understand why there is no gyroscopic effect? The propeller is spinning, and in that same axis of propeller spin, I am rolling the ship to the left and right. I don't get any problem. Okay. Clear? Why there is no gyroscopic effect in this third case when you roll the ship with the propeller going around? Okay. So this entire thing is taken from a Kurmi textbook from section 14.5.